Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In this video we will give an overview of DSO 138 oscilloscope, board layout, and main functions. So, let's get started. As we mentioned in our previous video, DSO 138 is small and compact oscilloscope, for beginners and enthusiasts who are just starting to experiment and learn about electronics and signals. It is a relatively cheap device that has basic functions for input, management and display of signal information. In general, oscilloscope is a device that enables you to visualize electric signals. In future videos we will go more in depth about signals, but for now, let's just define electric signal as a way of relaying information via conductor. This definition may be a little vague, so let's give you a few examples that will help you to grasp the nature of signals. Every change in occurrence in world around you can be a signal. Images that you see, sounds that you hear, temperature that you feel, sense that you smell, all of those things can be perceived as signals, depending on how you interpret them. If you perceive any of these changes in occurrence in world around you as a new information about something that you are interested in, then we can say you received a signal. When you are waiting to cross the street, change in semaphore from red to green gives you a signal that is okay to cross the street. For blind people, change in sound that semaphore emits can also signal them it is okay to cross the street, and etc. Since this video is dedicated to workings of an oscilloscope, we are interested in electric signals. Electric signals are the ones that are transmitted through conductor or wire. The information they carry is represented by changes of voltage or current of the signal. In other words, information that is relayed by electric signal is encoded by changes in voltage or current. How about an example of this? Picture a doorbell. When someone at the door pushes the doorbell button, the inner workings of electric circuit of doorbell sets into motion a few things. First, the push of a doorbell button closes the electric circuit, which as a result enables current to flow through the circuit, resulting the buzzer to activate and start emitting the sound. We can say that by pressing the doorbell button, the person who is standing at your door initiated an electric signal, that via buzzer that converted the electric signal into sound, informed you that someone is at the door. Now, there is nothing interesting in electric signal of doorbell to see on the oscilloscope, so are there any other types of electric signals that might be more interesting to observe visually? What about sound? Can we see sound? Is sound an electric signal? No. By its nature, sound is a pressure wave that travels through air, hits our ears, and then is interpreted by the brain as sound. Same can be said about light. Our eyes collect the electromagnetic waves that falls into specific frequency range we perceive as light, and then our brain creates image in our head. So, what kind of signals are there that we can see with oscilloscope? If we take a microphone to record a sound, from let's say a tuning fork, microphone will convert pressure wave that is sound that has been emitted from tuning fork, into an electric signal that we can send through the wire, or conductor, to amplifier, to be amplified, and that is one type of electric signal we can observe. If we attach the output from said amplifier to oscilloscope, we see a sinusoidal wave of certain amplitude and frequency displayed on screen. Now, in this modern day and age that we live in, there are devices called a signal generator, that can generate all sorts of electric signals, varying in type, amplitude and frequency. Some more advanced signal generators can generate complex signals, but for this video we will use 4 basic types of electric signals: sinusoidal, square, triangle and saw. The sinusoidal wave is more commonly known and referred to as a sine wave. It's just easier to pronounce, that's all there is to it. Now, the first, and always the most important question that you might want to ask, is why? Why would I want to see or observe an electrical signal? I can't think of a good reason out of hand, unless you want to modify or change the signal itself, and then, you want to see the result of your intervention. How about an example? You have a weak electric signal, and you want to amplify it. Here, you can counter and say, Well, why not generate a strong signal in the first place and be done with it? Well, simple answer, it takes a lot of power, and power is expensive. So, the guiding principle in electronic, like in any business for that matter, is to produce most result with minimum cost, in this case, cost being electrical power. If we take a microphone and record sound, the resulting electric signal is very weak, measuring in millivolts, and that is pretty weak. So, naturally, we want to amplify our signal, so that we can reproduce it later and hear it on big speakers. Here, you can intervene as well, and say, is it not enough that we can hear clear and loud our sound, why would we want to see it as well? Well, here is the catch. When recording and amplifying the signal, certain unavoidable noises and errors can creep in, along with our signal, and then, by amplifying the signal, we amplify those unwanted noises as well. Depending how good we can hear, we might not notice them at all, but nevertheless, they are there. When displayed on oscilloscope, those noises and errors are visible as distortion, in what would otherwise be a perfect sinusoidal and symmetrical signal. Also, when we observe our signal on oscilloscope, we can learn more about signal, and get a lot more information about signal as well. Alongside the shape of signal, we can get information about amplitude of signal, its frequency, duty cycle, in other words, we can see the resulting modification of our intervention in signal. You can purchase the DSO 138 oscilloscope as a kit, meaning that you will get a circuit board and bunch of electronic components, ICs, resistors, capacitors and connectors that you have to solder yourself. If you are skilled in this sort of work, go ahead and get that solder hot and start soldering. On the other hand, more easy way is to buy already assembled device. Here, you have two options, just an oscilloscope, or you can buy a protective acrylic case that goes along with the device. Our suggestion is that you spend an extra $1 or $2 and get yourself an oscilloscope with acrylic case. There is video on our channel where we have demonstrated how to assemble acrylic protective case for DSO 138 oscilloscope, so after you are done watching this video, go ahead and check it out. Alongside oscilloscope itself, you will get a probe. A black cable, with BNC connector on one side, that hooks probe to oscilloscope, and on the other side are two alligator clips, red and black, that are used to connect the oscilloscope to source of the signal. Black clip is for ground connection, and red clip is used to connect the oscilloscope with source of signal. Both oscilloscope and signal source should share common ground connector, otherwise you will not be able to see signal displayed on screen. Next, you will need a power source to power the device. Now, there are two ways to power the oscilloscope. You can purchase a 9-volt AC/DC adapter, with barrel connector, and use it to power the device. Other way is to use an independent power source, such as battery, and power the device using white connector on the board itself. Make sure that whatever source of power you choose, you match the polarity of power source and connectors. Also do not under or overpower the device by using higher or lower voltage power source. Using lower than 9-volt power source, you will not be able to get the oscilloscope working. Likewise, using power source higher than 9-volt will damage your device and cause it to stop working. If you are not using protective case, make sure that you do not place oscilloscope on conductive, for example, metallic surface. Bottom of oscilloscope contains a lot of soldered points for various electronic components. Short-circuiting them will cause device to malfunction. If nothing else, use plastic spacers that comes with device, to lift up the device from work surface. Counterintuitive, you cannot use USB connector to power the oscilloscope. In this version of the device, the USB connector serves no purpose whatsoever. There is a mini version of DSO 138 device that can be powered via USB connector. Now, the quality of your power source can greatly influence the display of signal and work of the oscilloscope itself. Cheap AC-DC adapters always introduce AC noise in power output. That noise is reflected as interference in display of the signal, producing rugged signal, with lots of noise displayed as stray pixels. If your aim is the most precise and true to original display of signal, your best bet is to use a battery. It provides power output free of AC interference. More about this in following videos. Let's go and give an overview of top board connectors, switches and other components that might be of interest to us when using oscilloscope on daily basis. On the top side, starting from left to right, we have BNC connector for connecting probe cable, for voltage reference points, AV+, AV-, plus 3.3 and 5 volt. When you purchase oscilloscope as a kit, these are used as voltage reference points to check your assembly results. Next, we have a 3.3 volt square signal source generator output. This signal generator output is used to calibrate device. Following, we have two power connectors, black barrel connector for external power source, such as AC-DC adapter. White is used for direct connection to power supply such as battery. Do not use both connectors simultaneously to power device. Use only one at the time. On the left-hand side, starting from top to bottom, we have three switches, marked CPL, SEN1 and SEN2. All of these switches are 3-point selectors, meaning they can be in one of three possible positions, left, middle and right. The first, top one, is CPL, which stand for couple selection. When switch is in the most left position, marked as GND, the input signal from probe bypasses oscilloscope and it is piped directly to ground connection of the device. The middle position of the switch, marked AC, is used to display AC portion of input signal. Now, AC is short for alternate current, and oscilloscope displays voltage, so there is something out of joint in here. Since input signal can have both AC and DC component mixed in together, selecting this mode of operation means that oscilloscope, through its internal capacitors, filters any DC component that signal might have, and displays only AC portion of the signal. Consequently, one would think that when we switch CPL switch to the most right position marked DC, we will get only DC portion of signal. However, in this mode of work, oscilloscope displays signal in its entirety, both AC and DC component as well. In the middle, we have SEN1 switch which stands for sensitivity selection. It also has three positions, marked 1 volt, 0.1 volt and 10 millivolt. As marking suggests, it is used to appropriately display signal in regard to its input value in ratio 1:1. Now this can be little confusing, so let's make it more clear. If you anticipate input signal to have point-to-point value in volts range, let's say from 1 to 5 volt, you will operate oscilloscope in this mode of work. The above-mentioned internal square generator produces signal that has 3.3 volt point-to-point value, so when you are calibrating your device, to get best signal display you will choose this mode. When switched to middle position, marked 0.1 volt, you are setting device to display input signal that has value between 0.1 and 1 volt, and at most right position marked 10 millivolt, you are setting device to display input signal that has value between 10 millivolt and 0.1 volt. Setting selector to wrong range will cause signal to appear only as line in the middle of the screen if you set selector to high value, or you will not be able to see top and bottom portion of the signal if you set selector to low value. And at the bottom, we have SEN2 switch, which stands for sensitivity selection as well, but this time it is divider selector. You can also think of it as display scale or zoom out factor. You may have noticed that the display has grid shown when powered. When SEN1 switch is in position 1 volt, and SEN2 switch is in position X1, that means that height of one square of the grid is 1 volt. When we switch SEN2 to position X2, with switch SEN1 still in 1 volt position, now this means that the height of one square of the grid is now 2 volt, and as you may have guessed, when SEN1 switch is in 1 volt position, and SEN2 switch is in position X5, that means that height of one square of the grid is 5 volt. To give you an example, if you have input signal that is 1 volt point to point, its height on the display will be exactly 1 square of the grid. Consequently, 3 volt signal will be exactly 3 squares of the grid, and so on. In real life, you can use SEN2 switch to zoom out display. For example, if your input signal is 20 volt point to point, setting SEN1 switch to position 1 volt, and SEN2 switch to position X1, you will not be able to see top and bottom part of the input signal, since the input signal is too big to fit on the screen. To fit the signal to display, you will zoom out the view by switching SEN2 switch to either X2 or X5 position. We will cover this in more detail in next video. Right next to CPL switch, we have two adjustable capacitors, marked C4 and C6. They are used for calibration of signal display. We will cover that procedure in separate video. At the bottom, starting from left to right, we have DGND connector, used as a ground connector for following V1, V2, V3, and TLVL test points. In test mode, when CPL switch is in GND position, V1 and V2 will be at 0 and 1.66 volt, respectively, to DGND connector to the left. Next, we have UART, also known as serial connector. Using these three pins, GND, TX, and RX, you can connect the device via UART to USB adapter, to your PC or laptop, to upgrade firmware. Next, there is mini USB connector, which, strangely enough, has no purpose at all. Next, we have a SWD4 pin connector, used for debugging purposes to connect the device, for example, to Arduino or Raspberry Pi development boards. Following is the trigged LED diode. Depending on selected mode of work, it flashes every time there is change in threshold level of input signal. And at the most right, we have a reset button, which when pressed, reboots the device. On the right side, we have 4 push buttons. At the bottom we have a CL push button. When pressed, it cycles through various settings: time base, trigger mode, trigger slope, trigger level indicator, horizontal position, and vertical position indicator. In the middle, we have plus and minus push buttons. They are used to adjust settings selected by SEL push button. And at last, we have OK push button, which doubles as pause and resume button, depending on selected mode of work, and also in combination with other buttons can perform additional functions. For example, when by pressing SEL push button, we select to activate adjustment of vertical position indicator, holding OK button for 2 seconds, centers the indicator in relation to input signal. Then, using plus and minus button, we can move signal up or down, to horizontally center the signal on display. At the bottom side of oscilloscope, the only 2 things that are of importance to us are jumpers marked JP1 and JP2, which when are short-circuited, enable firmware update, using UART connector. This concludes our quick overview of oscilloscope layout and its basic connectors, switches, and buttons. In next video, we will introduce external signal and demonstrate all of the functionalities of the oscilloscope. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.